wait for a couple more minutes.
Sure.
All right, and meeting is being recorded. Right, I'm just taking care of the recording. Okay, we have 17 participants. We're expecting maybe a few more.
Okay.
Okay, let me get started. So good afternoon, everyone. So thank you for joining in the current Power and Energy Seminar Series, also known as the current SLC Seminar. So my name is Han Chui, and I'll be hosting the seminars throughout the semester. Today, we're glad to have Dr. Kevin Tomsovic, our current Center Director, to kick off the seminar for this semester. Dr. Tomsovic's presentation today is changing testing and simulations needs for grid modernization. So about Dr. Tomsovic, Tomsovic is currently CTI professor in the Department of ECS at University of Tennessee and director of CURENT, a NSF and DOE research center. He received the bachelor's from Michigan Tech University, Houghton in 1982 and MS and PhD degrees from University of Washington, Seattle in 1984 and 1987, respectively, all in electrical engineering. From 1992 to 2008, he was a professor at Washington State University in the Department of Electrical Engineering and Computer Science. Visiting university positions have included National Cheng Kung University, National Sun Yat-sen University, and the Royal Institute of Technology in Stockholm. He held the Advanced Technology for Electrical and Energy Chair at Kumamoto University in Japan from 1999 to 2000, and was a program director at the NSF in the Electrical and Communications Systems Division of the Engineering Directorate from 2004 to 2006. He is a fellow of the IEEE. So for now, let me turn the presentation to Dr. Tomsovic.
Okay, thanks, Antal. And so today I'm going to talk about simulation and testing, and part of that I'll talk about the current center and our test beds in the center. So there may be some point there where Hantal's better able to answer the questions than I am, because he's in charge of the large scale test bed. Otherwise, Hantal, is there any bookkeeping things you have to do with the seminar in terms of keeping track of people, or just they sign in by logging in, that's they're there?
Yeah, thanks for reminding me. So students and attendees, so if you're taking our EC 496 and 691 for credit, please locate your name. If you haven't logged in with your real name, so please do so by clicking on the participants tab, participant icon to open the tab and rename yourself. You can find it in next to your name, and there's a more and rename option. I will take a screenshot of the attendee around like 12:30, so that making sure that you're logged in and with your name are recorded. Other than that, and we are also looking for maybe a few more student presenters. If you are interested in presenting, just let me know, or let Hao Yuan Son know. So I think that's all.
Okay, great, thanks. And I will, people feel free to jump in and interrupt me if you have some questions. I mean, I'll leave the chat box open, so if you have a question, you want to put it in there, that's great. So, okay, so testing needs here. I'm having trouble with it. Oh. mouse. Okay. So first of all, what is CURENT? I know some of you have been here a little while, so you probably know some of this. But anyway, we are what is called an engineering research center. It's more or less the biggest investment that NSF makes into a particular area. So it's different than NSF normally does because it's over a longer period of time. It's up to 10 years. This is our 10th year. And then we leverage that base funding for more. But so we do about $10 million a year in the center, 10 or $11 million a year. This is the only ERC that's been devoted to power transmission, so we're pretty pleased with ourselves for that. You know, that's a broad program, so there's lots of things on medical devices, chemistry, and so on. But this is the only one on power transmission. And then there's 4 universities here. That's UTK, Rensselaer Polytechnic, Northeastern, and Tuskegee. Okay, and we have an industry partnership program as part of the center. That number's a little bit off. I forgot to update, but we're about 35 members. Right. So, and we're quite large. So I just wanted to introduce a little bit about that, the CURENT center, before I then start talking about these testing needs. So the main theme of the center is this idea of wide area power control for the grid. And here the idea is that if we want to really take advantage of renewables, then the best places for renewables are often not near load centers, particularly for wind, but even for solar to a certain extent. And then you got to move power over long distances. Then moving power over long distances is not that difficult. You just have to get the voltage very high. However, because of the intermittent nature of solar and wind, it's more dynamic and there's greater uncertainty. And you don't want to just put up massive transmission that goes to waste, because transmission is expensive. Okay, so I don't know, sorry, these windows popping up on my screen. I'm not sure if you can see them, hopefully not. The different sort of technologies in the center then that are kind of driving things is one is around measurement and monitoring. There's many more things that are monitored today in the grids, from weather variables to water and hydro systems. But the biggest thing probably is using the GPS signal for synchronization, so that we can get our voltage and current phasors synchronized, and that means we can directly measure their magnitude and phase. And if you know the magnitude and phase, then you know the state of the system directly. So that allows you to, monitor the grid and take actions. Well, these devices, it's 30 times a second, but the state of the grid, several times a second, or it's updated several times a second, as opposed to historically where you may not run a state estimate of the grid for 10 minutes or 30 minutes even. So you can push the system closer to its limits. The other thing is the communications is changing. So now we're more interested in distributed communications, not point to point as it is in the current operation of the grid. Things are hierarchical, basically 1960s, 1970s design for control centers hasn't changed that much from after the New York blackout in the 60s. It's a polling system. And then the other technology that is critical for what we do in the center is actuation. And by this, we mean anything that can affect power flow. So it could be traditional devices, but really the one we're concerned about is power electronics, or the one we want to take advantage of is modern power electronics that can much more quickly and much more much more flexibly take action on the grid. Okay, and here's sort of where we are in CURENT. Like I said, we're in year 10. So we're in what we consider generation 3, and that means that we're looking at very high levels of renewable. So for the most part now, people are regularly talking about more than 50% of energy in North America in the next 10 to 20 years being delivered by renewables, and that means greater than 80% instantaneous at times. And here in renewables, not including hydro or other types of renewable fuels like wood products and that. since they run off a more traditional unit. So this would be 80% of inverter-based renewable. We think in this generation where we want to take advantage of a super grid or an HVDC overlay, moving power potentially east and west in the United States. You can get the rights of way, controllable loads, converter-based for response. Lots of monitoring, even down to the distribution system, including PMUs, line temperature, and so on. A great wealth of information. And then something we added in the last couple of years is starting to think about automated system restoration from outages. So how do you restore the system when it was down if you've got a primarily power electronic driven system? All right, and our overall philosophy in the center about the control and coordination or the architecture for this is we think the future system has to be distributed because you have so many numbers of renewables, you can't pull all that information in a control center and do your computations there. So decisions have to be made in some distributed manner. However, it has to be done in a way of supporting the center. You need lots more measurements because things are less predictable and you have to be able to adapt to the data that's out there. So it's data driven more than it's model driven. You need some sort of modular structural system. So it's not centralized, but you still need devices to act in a consistent way. So maybe this is, droop on frequency on not only generators, but loads and even inverter based sources to help you with frequency support like you would normally have with a governor, but you still need that sort of modular structure. But we also aren't a center that says, everybody's going to go to rooftop solar and we're not going to share resources. So the way to get a robust system, and the reason we have the grid in the first place, well, both for economics and for robustness and reliability, is to share resources. So we want the grid to be there. Okay, so the rest of my talk, I'm going to be emphasizing this idea that test beds can be an central organizing feature for research. This is one of the tenets of the ERC program also, in that if it's a device thing, you maybe not necessarily a test bed, but you actually build the device. But for a center like ours, which is trying to modernize the grid, you have to have something that creates the right environment for that. You can test out new ideas and then learn where things fail and make changes to your system. And you need to be able to do this in a very relatively simple way and comprehensive way so that your research is can progress quickly and can be done meaningfully. And then I'm going to wrap up at the end then with a little bit on concepts of resilience and what the new testing needs are. So that'll be an add-on to this kind of idea of lots of renewables, and that's kind of the direction the center has been moving the last few years. Okay, so here's the things that are sort of changing in the power grid, and all these affect our ability to do testing and simulation in a way. So we're moving from large central generation to smaller units, so many more units. Units that are inverter interfaced, as well as loads that are inverter interfaced. More actively controlled transmission, so this generally would be for power electronic type devices, fax devices, or could be through HVDC things. More sensing, open communication, market driven. So if you're not familiar with the history of the grid, things were more or less cost driven, meaning that you try to do low cost type of optimization for much of the history of the grid with reliability as constraint. And then in the late 90s, around the turn of the century, things moved to a market structure where things are done by bidding and trying to put pressures on the system to get efficiencies from a market perspective. And now that's going even more extreme, where it may not even be part of the centralized market, but you could have a distributed market. So many devices contributing to that. Okay, and then historically we were focused really on reliability, or reliability as a constraint in the grid. And now we still want that. We still want things to be economic and reliable, But in the last 5 to 10 years, this idea of resilience has become more and more important. So can you recover from extreme events? Can you get critical services out from extreme events? And I'll touch on that at the end, depending on how much time I have. Okay, so all these things, and I'm not going to go through every detail here, are changing the way we do grid modeling. At first, there's so many more devices, and now they're power electronic devices. Those have very high speed response. So we try to model the details. Certainly the switching inverters, you could never scale up to the size of the system we need. It also has different sort of electrical characteristics. The familiar electromechanical coupling that we have in the grid is lost with power electronic devices. We also get new sort of load response. Traditionally, we know kind of how a motor acts, which is a big part of the load. Lighting is more or less resistive, but a power electronic device or variable interface, like say for a variable speed drive, it can have any sort of characteristic that the manufacturers program into it. So I said I won't go through all these, but then now much more reliance on communication. Historically, the controls were all local. If you're trying to do your simulations, you could just sort of assume instantaneous measurements and that, or a small time constant for the measurement, and you were fine. Now you have to worry about the latencies in that communication system and bandwidth limits and so on, and of course cyber security concerns. And then finally, well, not finally, two more things. The other thing is that historically we've separated out transmission and distribution when we did large scale system studies, because the distribution we just do it as a lump load of some sort, and it wasn't actively controlled. But now it is actively controlled, and also it could be an area that we have lots of generation. Say if you've got some rooftop solar on that. So it's difficult to just throw that all into one big model. So we have to rethink a little bit of how we do that. And then finally, when I mentioned about reliability and resilience, historically we have a pretty good idea of what we have to do for reliability. You lose a large generator, is the system fine? If you do the longer term studies for reliability, you'd say, well, what's my availability, my generation? Can I meet the peak load, forecasted peak load, and with some probability things? Resilience is a little bit different. I mean, how do you, first of all, you can't design for an extraordinarily extreme event to have no outages. It's just not possible, or it's cost prohibitive. And secondly, it's not necessarily clear what things or what events you have to model, right? So if you're California right now with their fires, what sorts of things should the planners be modeling? What can they sort of plan for? Or right now with Hurricane Laura coming up through the Gulf, the exact place it's going to hit makes a big difference in terms of the impact on the grid, and you can't really just try to think of any possible situation and then do a whole bunch of simulations. So this is it's an open area, and Department of Energy and other agencies are quite interested in trying to think about what's the best way to do that. Okay, so now talking for next part of the talk, I'm going to focus on what we do in Current and what we're trying to do with our tools there. So we have two major test beds. The large scale test bed, which is got a component of it which is similar to what we normally do in power systems with positive sequence models of power, like transient simulations that you would do in PSSE or TSAT or Power World, standard commercial tools. But we've added some things for this future grid that we see that are critical. So we'll go through that. The other thing is we feel like if you really want to evaluate these future scenarios for the grid, you need to have some hardware, because hardware reveals your real ability to integrate different components in a much more realistic environment. Now, hardware in this case is going to be an analog emulator, sort of like an analog computer at power, but more importantly, it has all the components. It's like a mini grid with some grid characteristics. Now, it doesn't scale well. You can't go up to thousands of buses without, you know, requiring a massive amount of inverters, but it does give you ability to test different things. Okay, so what are our objectives for these test beds? One, we want to provide some platform that make it easy to integrate new technologies and really be able to test out new control algorithms. We want to understand different power electronics technologies and how they're impacting the grid. So historically, we don't model those with any detail at all in our power system simulations. We need to include communications, so that's more important. We want to understand network security. We want to develop scenarios about resilience and high penetration of renewable scenarios, unusual scenarios of weather, maybe multiple days of extremely hot weather, what that means. And then other developed control algorithms. Okay, so on the LTV, what we're really doing different than your traditional power system simulation is we're providing a closed loop real-time testing environment. So historically in the grid, there's not wide area closed loop controls. Any closed loop control would be at a plant level or a bus level. At the control center, which they do is gather information, they schedule things, it's essentially open loop, with the exception of AGC, or the load balancing function. But that's a very slow control loop. It doesn't really need fast communications or advanced communications. So that's not quite the same thing. So, but we want to be able to provide that. We want to understand how measurement devices can be in error and how they can introduce problems, how they fail, and how that's going to impact your controls. And in general, just provide this platform for cyber physical simulation with renewable generation and power electronic models. Okay, so this is a little bit of a philosophy in terms of what the LTB is going to do. And we're trying to pull together these different things that would not normally be in that power system simulation, which was just focused on that power system components, right? Now, if we think of two different ways you can go about this, you can do the sort of, well, I know how to do transmission, I know how to do power electronics, I know how to do distribution, I know how to do buildings. I've got those separate simulators and I can just try to glue them loosely together. So this is sort of best represented by the Helix approach, which is a program at the national labs that DOE has pushed. So the good thing about that is that you can kind of glue these together and it's simple and everybody can focus on what they do best. The problem is that you may not be making similar assumptions on these. You've got different timing on these, and the coupling here is very loose, and it's not clear that you're actually getting something meaningful out of this, right? Or you're not sure what the impact of these different, just stick these models together, whether you're really testing anything. Okay, so you can go the other extreme, which is, I would say, the Modelica type of approach, which is a software tool for doing simulations that basically allows you to throw everything in there. It's got some very, very powerful numerical algorithms for stiff systems, systems with lots of different time constants or range of time constants. And it puts everything into one big model. So that, because of the powerful algorithms, it's got some decent functionality still here. However, this requires each individual researcher to have pretty broad knowledge and extensive experience. And even with the powerful algorithms, it's not clear to me that you can really scale this up in this type of approach without starting to sort of fall apart of this. So we're trying to split this a little bit. So we're sort of incrementally adding things to our basic power system engine, like the communications, the measurements, with some restrictions on how we do the modeling. So this is our hybrid approach. So if you look at this, what it's trying to represent is that the power system simulation part of it and the communication simulation and these other components are independently developed but they have to talk to each other in a pretty integrated way. And we do this just through streaming data. We developed some streaming protocols for them to interface each other. And then we can be somewhat agnostic about what the simulator is. So on the left side there, you can see we have Andes, which is the in-house simulator that's Python-based, developed by Hantao. We can use commercial tools like GridDyne from LLNL or ePhaser Sim from OpalRT in Canada. But they just have to be able to handle that interface and stream out the data that they would get from that simulator. And then, you know, we can do our scenarios and some independently, other models. We sort of glue on this EMS system, basic EMS functions. We could even use, we haven't done much of this, but in theory, we could be using commercial EMS systems. We have the commercial EMS systems here. We haven't really done much with them. Or we can just kind of plug in our individual control projects. So the idea here is to simplify what the researcher has to actually know on that, but have all the other components in there so that you're testing things in a fairly rigorous way. Okay, so here's our basic design considerations. You know, we really want it's got to be interoperable, so we have this plug and play sort of architecture. We want to be able to test measurement-based control integration, so we have to have simulation ability on actual measurements such as PMUs or other types of measurements. And we want to be able to scale up. This, we're not doing extremely large models for trying to get in real time, but if we use a commercial tool like ePhaser Sim, maybe we can do 1,000 to 2,000 buses. It's not really possible at this point in time to do tens of thousands of buses for if we want to do real time. Although we can do those if we're not as concerned about real time and hardware in the loop. Okay, I'm going to skip over a couple of these slides here because I'm a little bit behind, but these are just describing, and these slides will be posted. You can look them up. These are different, some of the different simulation engines we have. The one developed in-house, which is has got a ability. It's probably its biggest strength is that it's got this hybrid structure of symbolic processing and integration. It allows us to develop models very, very quickly. Maybe Hantao will give a seminar in detail on this sometime later. We've got PMU models in there with error distribution. We've got visualization system, which not quite what one would see in a control center. We want to do something different. This helps us visualize events as they occur on the grid. I'm going to show some example of that. So it's not like the one-line diagram you would have in the control center, but it's actually better for what we want to do, which is to visualize disturbances on the system. So in terms of modular architecture, I'm going to kind of be brief on this. We've got DYNE, which is this distributed measurement environment. So that's this development we had for gluing together these different things. So it's a way of passing data between the different modules and allowing them to be integrated into the simulation. And then we have our communication network emulator, which we call LTBnet, which again is using streaming protocols to put them together. So for that, we have the communications. We can do fairly detailed network emulation, including doing cybersecurity. So a component of it, and won't go into details of this. This is showing the streaming server and how it glues together different things. One thing to point out here is that we do try to use standards, such as like the OpenPDC. So we're trying to get this environment to be as close to the real environment of control and operations for the grid as we can. So I'll skip over this, and I'm going to get to a couple of simulations to show you what this might look like. So we've got a model of the North America. Of course, this is highly aggregated or reduced quite a bit. It's about 1,000 buses, where the real system is, depending on the most recent model, it's about a little over 100,000 buses if you include ERCOT, WCC, and the Eastern Interconnect. So it's highly aggregated. It's this future system where we've added lots and lots of wind. more than 50% in each interconnection. We've got around 30% PV. This is in terms of capacity. So it's a fair amount of renewables, and then it's also got this HVDC overlay. And the idea there is that if we did have an HVDC overlay in the country, which we don't right now, we just have a few DC links, but that would allow us to move power east to west. And that would give us the advantage of taking advantage of diurnal cycles, right? So when the sun's going down in the Midwest, it can still rely on the power that would be coming out of the West. And there's been studies that show that it's very economic to take advantage of those sort of shifts if you can go east-west. So I mentioned that we have long-distance power transfer in the US, but for historical reasons, it goes north-south. And then the three interconnects, WCC, ERCOT, and EI, are only loosely connected, so you can't really transfer power between them. So let's show a couple of simulations we can see on this for fun. This is one using wind inertia to provide some frequency control. And you'll see a disturbance down in LA, and then in the uncontrolled case, since there's not normally damping controllers on the wind units, goes by a little bit quick, I'll do it again. Then you can see that in an uncontrolled case that oscillations continue a little bit longer. Oops, let's go. So there's disturbance, and you can see on the left, on the right, those oscillations die out quicker. There's also over in the eastern interconnect, you can see a poorly damped mode out east. So that just, it's probably not significant for this disturbance, but it does show that we're transferring power between the different interconnects and giving it some coupling of the dynamics, which is not there today. Okay, here's a damping control example. Actually, that last one was emphasizing, I thought it was, I forgot it wasn't damping. That one was inertia, so the depth of the swing is reduced by the control case. This one will show more clearly the oscillations. And this is, again, using wind generators. So that's something they would normally not be used for, but to help with control. So on the left, you can see it's poorly damped mode in the southwest there ongoing, and you can see it's died out in this. This is only showing WCC in this one. So we're not looking at the HVDC overlay. Okay, so again, the important thing here is in this environment we've got is that it's a fully integrated model, so we can test out these things and hopefully do a comprehensive thing. These are all from earlier demos we've done at the annual site visit. Okay, this one is going to show cyber attack, and then it's basically providing misinformation to the operator, fooling them to think that the system is it's a replay attack. They think there's a major disturbance, and then causes the operator to do a system separation, thinking that the system is had a major bring up. So on the left there, you can see the frequency deviation. Once it gets a threshold, then the operator thinks the system is going to exceed its limits, and then opens up some tie lines, and then you can see it separated into things. So this is, again, just showing a frequency plot. So you can see that now I've got an islanded system and some load loss. Again, this is a point to show that we've got an integrated system where we can model communications, in this case, a cyber attack on communications. Okay, so the other test facility we have, or test bed, is the hardware test bed. And this one, the idea is we're going to have to aggregate much more, but we want to use real power signals. So it's a three-phase system that has characteristics of the grid. I mean, it's got similar frequency and dynamic performance, but it's going to be highly aggregated. What's good, though, is we'll be using actual measurement devices. We can use protection and can put everything in there. The visualization on this is going to be a little bit more similar to what you would see in a control center rather than the wave type of phenomenon we can see in the other one. Okay, so with this, what we do is we don't want to actually, provide power to load. So we're using a circulating system. So all we really have to do is supply the losses in the system. So that allows us to go to a higher power system. I said it's a not high power, not what a power system person would consider high power, but it's a three-phase system. I think right now we're running at around 50 amps or 70 amps, something like that, and 100 and some volts line to line. So it's not trivial, but it's not high power from a systems point of view. But that is enough power that gives us to use actual, devices, communication devices, measurement devices, CTs and PTs, so on. And all the dynamics are emulated with inverters. So this is an older slide from Fourier's system. We've made a bunch of changes recently. You'll see that later this year, particularly when we get closer to site visit, the latest stage of that. But we've got a control center. This is down in the visualization room on the first floor. If you haven't been there, you can go take a look. This is representing 4 areas from the WCC system. The reason we have different stations is there are multiple areas in the Western Interconnect that can be used, that only see parts of the system. So we try to emulate that. And the display here is really just for demonstration purposes, and the stations are what the operator would see. Okay, so what does this get us? For one thing, it gets us broad timescales in one system, which you can't really do with software. Since this is real hardware, it's not simulation, it's not doing computations of it, it's actually running, and it's sort of what I would call true parallelism. And in fact, you never get true parallelism in a software, even a high performance community environment. Things are still being scheduled. But these are actual devices running with certain characteristics. Right? So that doesn't, the hard part, of course, is then you have to have hardware, so it's difficult to scale up to large numbers. But if I've got power electronics that are running in microseconds, that's fine. It doesn't slow me down for my other devices that may be working in the millisecond time scale and so on. It allows me to integrate the real-time communication, control, and power. And then I can program my converters to emulate just about anything. I can make it look like traditional units, or I can make it look like a inverter would be on a wind or a PV system. Again, this is an older slide. I forgot to update it from fall, but we've got a few more things in here. But we can do all sorts of generators, traditional synchronous generators, wind turbines, type 3, type 4. So type 3 is a DFIG, type 4 is a full inverter-based system. PV, we've got batteries, emulators, HVDC. We can interface to other digital simulators if we want, such as the RTDS. And one thing that's, I think, particularly interesting is that we can actually emulate transmission lines of different sizes and lengths. So part of what we do in the hardware test bed is we just use an inductor. An inductor is a fairly good model for a transmission line. However, then it's not very flexible, or in order to make different types of lines, you've got to do switching, which we can do some of that for different systems. But the other thing one could do is use back-to-back converters to emulate the AC line and get the same sort of characteristic. So we have several lines that we could do that with, and we could do an experiment like, okay, well, if there's, these two areas were further apart, then we'd have greater reactance between them. We could see how that would impact the performance. And we could also do things like faults. That's probably even more important than that. But the changing line is something we might want to do if we were looking at different systems. Okay, we've got all functions that you would normally have in a control center there, the regional level, the central level, local level, so protection. And I'm not going to go through all this stuff, but so it's fully comprehensive. It's trying to look like a fully operating grid, or emulate that fully operating grid. And then this is just to highlight a few things that you can do with that you could never do with a pure software system. is we discovered, actually, students discovered when they're putting things together, of some harmonic resonances. So these would be much higher frequency than you would ever try to simulate in a power grid. And you'd find these instabilities that you wouldn't have normally found unless you had actually hooked up the hardware. And these are real issues. There have been cases in Europe, Germany, and in China where I think they're for offshore, but I'm not necessarily sure they're offshore. But they're weakly interconnected renewable resources through inverters that these resonances popped up. So it does reveal things that you can't normally see. This just shows the line emulator that we do. Like I mentioned, it's a back-to-back DC, and then we can sort of schedule it in terms of what it would look like. So in this case, that's down there. That's a Condor's two-area system that represents Ontario Hydro. That should just be either dropping out a line you could do for line fault, or if it just the line cleared, you could suddenly increase the impedance to what it would look like if you just lost the line without a fault. Okay, I'm going to skip this. Okay, and then just to show that we're comprehensive here, we do have this normal system protection schemes that you would have on a system. Again, something that you don't normally have in a power system simulation, just because it slows things down too much. This is things like under frequency load shedding or over frequency load shedding, those things that are common throughout the grid, but usually people don't model them in their studies. But this is a fully integrated system. And I mentioned that you can integrate with a digital simulator. So the RTDS is a real-time digital simulator, three-phase, but of course it's digital and it's low power, so we just need to have an amplifier that goes between the two environments. Again, I'm being brief on these to kind of show. This, we're in the process of moving this, but this shows that we did the highly aggregated model of the Western interconnect. So this is all in the hardware test bed, what you see in brown. And as well as the green, which is the HVDC links over here, and in the red, that's ERCOT, again, highly aggregated, but those are all done in the hardware test bed, and then in blue is the RTDS. So we have for purposes of doing test runs, we have the entire North American system. Okay, just one other thing is that since this is just like a real system, we can program this to do other things. There's one project run by the Power Electronics Group under ARPA-E, and for EPB in Chattanooga that's doing a microgrid out at the airport. This just shows a simulation of that. So it is flexible. Okay, so I'm going to take 3 or 4 minutes and just sort of wrap up on the scenario development and resilience, and then open up for questions. So I mentioned at the beginning that I think this is going to be an important part of how we do testing of new ideas for the grid. And so the question is what sort of things should be studied? Heat spells, low wind scenarios, what sort of extreme events, hurricanes, fires. And the one thing you have to do is talk about what is the difference between resilience, traditional security, and that. So one is this idea of time variability. So the system is changing through that. That's not something we normally think about in terms of reliability, especially during the system recovery. We may be repairing certain things and having them come back on. The parameters describing the events may be changing, makes it harder, like sort of like it's a hurricane, both the wind speeds and where it's going to exactly hit is very dynamic. So we also need to explicitly model control actions, which we don't often in traditional power system simulations. They're sort of assumed, but or there's standard things that are taking place, but in this case, there may be some severe remedial actions taken, and those have to be, those interventions have to be modeled. And then another important issue in this whole thing is the economics of it. generally speaking, it's understood that reliability is something paid for by the customer because it's manageable, while resilience has to be some sort of social contract, because there's no way that individual customers can pay for high levels of resilience. It has to be socialized somehow. Okay, so why are we talking about this? I guess I touched on this. Is extreme events, weather events are increasing. Now we're also exposed to cyber attacks, so those could cause significant damage, at least in theory. People are postulating various physical attacks. I think that's a little bit harder to actually say. I mean, there's state actors who could do physical attacks, but generally speaking, most physical attacks are isolated incidents, not something that would go under resilience. Okay, and another important aspect to this is that if you're going to model these things, you probably have to start including other components of the infrastructure. So we've talked about with current in our large scale testing, we've got communications and IT and electricity, and it helps us out some. But when you think of really extreme events, then you have all the others, whether it's oil or natural gas or transportation that get involved. So we are going to start doing some work along these lines. Probably the most obvious one in terms of power systems to consider is natural gas supply. So there have been several events where there's extended cold snaps, and then the natural gas supply became limited, which in effect limited the availability of electricity because there's so much natural gas today for generation. So without modeling those things, in some sense, then you wouldn't have been able to pick up that vulnerability to an extreme cold snap. Okay, so some just quick definitions of for resilience. This is coming out of other fields. It's still being, sort of agreed on or debated back and forth in power systems. Conceptually, it's this idea that I can absorb some sort of extreme event, reorganize, restructure myself, and then learn and adapt and be able to continue functioning. Technical, it's more of this idea of got changing conditions and then try to recover rapidly from the disruption. So that recovery process is very important to that. You see different things on this. Like I said, these are all still being developed. It might be, this idea of I've got some sort of index. This might be the percentage of load I'm able to supply, or critical load that I'm able to supply. And then during the disturbance, like during the storm, certain things that I need, or then maybe I'm not too worried about, say, traffic lights. It's not a critical load during the disturbance. Then after that disturbance, whatever the storm is, I get this post-disturbance state where I start trying to pick up different things, trying to bring in more my critical loads. And then I've got a restorative state and hopefully bring everything back. Often you see this diagram where it comes back to some reduced level of performance. So just kind of finish up then. So if we start thinking about this resilience on top of what I've been saying about our test beds and the future with renewables, is there's a number of open research questions. What events do we have to consider? It's going to be system specific. We don't study hurricanes for California, but there's all sorts of other things, earthquakes that are occurring in unusual places. So maybe we have to rethink those. What things do we have to model? Is it realistic to model each infrastructure with some detail, or can we just kind of get the dependencies somehow? And then how to integrate these models. And then a very critical question is, can we even validate this? If we build up these huge models, then we may not be able to validate the results, meaning how do we know that what they're claiming is true? Okay, so I'll finish there. This is just some of the supporters we have in the center, acknowledge them, and NSF and DOE as we do. And then just a list of, well, this is old, so I'll put this back and just let's see if I get open questions or something. I'll just go back to here and open it up for questions.
Thanks, Dr. Tomsovic, for a great presentation. So, audiences, if you have any questions, you can raise your hand, and I'll ask you to unmute. So, let me begin with a question. So, Dr. Tomsovic, what are the greatest changes in the grid that you see in the past decade that might have a long-lasting impact into the future? And do you see any disruptive changes that just emerged recently?
Well, I mean, I think the one that's emerged over the last decade has been all these inverter-based resources and the changing characteristics of the load. So we do you do already see those events resulting in new ways that things can have outages, right? So that was like the UK system with their major blackout that was caused by, now I'm going to forget the details, but the trains went off line for several hours, and so that was a frequency excursion. Would have probably happened, 10 years before that, based on that. So that, I think inverter-based ones are probably the biggest change. Then I guess the other thing is what I'm wrapped up with, this idea of resilience, and that's not really so much the grid changes. It's just the environment that we're in with more extreme events, and then with more extreme events, there's it's harder for any individual utility to really prepare for those things. There has to be greater coordination there, and maybe rethinking how they operate. Good example of that for the fires in California, where there's actually communities that just disconnected from the system and had their own microgrid, and that way they didn't have to worry about disruptions from lines being shut down due to the potential fires.
Thanks, that comes like. Is there any question from the students or audiences? If not, I think that may conclude the seminar.
Okay, well, thanks everybody for listening, and if you have any questions, feel free to email and talk to me, and maybe some of the things in here, like I was gonna be mostly an overview, but we've got a lot of students who've worked on this, and maybe some of them will give more detailed seminar on some of these issues we touched on. So.
Thank you very much. And thanks for calling in, everyone. So we'll see you next Friday.
Okay, bye.
Bye.
Thank you.